would like to start with something that is known maybe to everybody, namely the Fick law. And this was, let's see, there is something that is not working. This is, Fick established this law in a very nice paper that I found it in the web, actually. It was a paper of 1855. And he presented this his famous law governing the transport of mass due to diffusion. And then he mentioned in his paper the experiment of Graham, which dealt with measuring a concentration of flux of salt that was diffusing between two reservoirs through tubes of water. So this is the Fick law. So the current is equal to minus the diffusion matrix times the gradient of the salt concentration in this case. So this, in other words, what I want to underline is that this law says that the flux goes from regions of high concentration to regions of low concentration. This is like the Fourier law, and in fact, Fick observed that his law was exactly the Fourier law for mass transport. So it's well known that the Fick law has been rigorously derived from boundary-driven stochastic interacting particle systems and in the stationary regime, say. In fact, the setup is a box where two different, I will speak about my order parameter, I will call magnetization, because I will speak about spin system in a while. So as I was saying, the setup is a box where you fix different magnetization densities at two of the boundaries, so left and right, say, boundaries. So you wait, a stationary state will be reached, and since you have these boundary conditions, the states will have a non-zero current. So this is the reason why it's called NES, this non-equilibrium stationary state, is because of its difference with the thermal equilibrium state where there is no current. All right. So the point of my talk is to discuss what happens when there is a phase transition. And what I will underline are the differences between NES and the thermal equilibrium. I mean, the phase transition, the phenomena in the phase transition at thermal equilibrium have much differences with the one for the NES. So you should have in mind an Ising model, so plus and minus spin, the usual Ising model nearest neighbors. And so the system has two pure phases. So if you impose plus and minus boundary conditions, the NES will have an interface. The structure is, as I will discuss with you, will be very different from the equilibrium, from the one in equilibrium. Actually, more surprising fact happens, like what is called uphill diffusion, meaning that the flux, the current, goes from regions of low concentration to regions of high concentration. And then also there will be more than one interface. Actually, we will see there will be three interfaces. So that's what I want to discuss with you today. And the model I will consider is a stochastic Gisborne-Landau model. And this is not just an example, because the restriction to Gisborne-Landau models is essential. Because for these models, we can produce an explicit expression for the non-equilibrium stationary state. Okay, so what I'm doing now is recalling you what is this Ginzburg-Landau stochastic process. And so take in mind, I mean, take a cube, say a cube, lambda n in ZD of size 2n, and then 2n plus 1. And then I will maybe consider later two dimensions. So, okay, but what I'm going to say is true also in more than one dimension. So the phase space I will be this one. So the variables are continuous variables. So phi of x is a real number for each x in lambda n. And the Hamiltonian is this one. So you have a one body potential and an interaction, which is the usual one. So it's the sum for x and y in the cube at distance 1 of the difference between phi x and phi y to the square. So for instance, you may think of u as the usual things you use in phase transition, like phi of x to the square minus 1 to the square. So this is the setup. And the evolution is so it's given by this generator that I call L bulk. It's the sum for x and y in lambda n close to each other by 1 of this generator Lxy. And Lxy has this form that you can see in this line, in this formula. And okay, this Lxy describes a process where the sum of the two variables phi of x plus phi of y is conserved. And then there is an exchange of magnetization between the two sides, x and y. And this exchange has a drift, which is this difference of the Hamiltonians. And the effect is to decrease the energy and forcing the two values, phi of x and phi of y, to be equal. Besides this, there is this term, which is a random exchange of magnetization viewed by a white noise. So for this generator, you have a conservation law, but I want to consider boundary-driven stochastic evolution. So the usual way to simulate reservoir is to add processes at the boundary, at the two boundaries. So these processes are, I mean, to define these processes, I consider these two generators, L plus and L minus. So L plus acts on the right. So when the x dot E1, so the first coordinate is n, and then L minus on the left when this is minus n. And so you still here also have a drift, and then you are somehow imposing the two, say, I will call it external magnetic fields, lambda plus and lambda minus, lambda plus on the right and lambda minus on the left. In the sequel, I will always consider lambda plus a positive number, and lambda minus the opposite. Okay. So, so the observation is that the complete dynamics, namely the one with the back generator at these boundary processes, is such that if you take lambda plus equal to lambda minus equal to lambda, the Gibbs measure, the Hamiltonian I presented to you before, plus an external magnetic field lambda is invariant. Actually, this is reversible with respect to the old generator. But as I said before, if L plus is not equal to L minus, we can compute explicitly the expression of the invariant measure, which is our non-equilibrium stationary state. This is proven in a paper with Hall and Presutti. And the theorem is the following. So if lambda plus is different from lambda minus, the invariant measure is a Gibbs measure with the same Hamiltonian as before, but with an additional slowly varying external magnetic field, lambda n of x. This lambda n of x is a linear function that interpolates between lambda plus and lambda minus in the E1 direction. So it's given by this. And moreover, you can compute the current in the stationary state. And this is negative, and is minus the gradient of this lambda n. So keep in mind that I will always consider lambda plus equal to lambda positive, lambda minus minus lambda. So this expression for the magnetic field will be just this function. So the observation is that the non-equilibrium stationary state in this boundary-driven Gibbs-Landau processes is still a Gibbs measure. But so we have a different Hamiltonian with a slowly varying magnetic field. Somehow we may conjecture that also for other models, the NES is close. Maybe it's not, but it's close to a Gibbs measure of an additionally slowly varying magnetic field. Somehow this is the hypothesis of local equilibrium that is used and proved in many cases in the analysis of hydrodynamic limits. Maybe you can see the discussion of this in the Yao paper, for instance, this one. Okay, so having this in mind, namely that the Gibbs measure with the slowly varying magnetic field is the NES, we exploit this to study what I said before, phase transition, situation in the presence of phase transition. And this I will restrict now to really Ising, the usual Ising model, nearest neighbor, for which we know a lot about phase transition in equilibrium. Actually, this Gibbs measure is actually the NES for the stochastic phase field model. That this is a class of models introduced by Bertini, Buttari, and Rudinger in 1999. And in DOP, in the previous paper, we proved that the Gibbs measure, the Ising Gibbs measure is the NES. I don't want to present this other model because I don't have the time. But I mean, the point I want to stress is that we have a Gibbs NES, which is a Gibbs measure with a slowly varying magnetic field, and we can study phase transition. So this is the setup now. Now I want to consider two dimensions. So I have a cube, a square, n by n. I put periodic boundary conditions on top and bottom. And then I consider this measure mu n, which is what I said before, the Gibbs measure. The Hamiltonian is the usual Ising nearest neighbors Hamiltonian. And then I have the slowly varying magnetic field, which is this one. So it's lambda x1 divided by n. And consider lambda positive. So in this paper with the online resources, we consider, we prove that for beta bigger than the beta critical, this measure has a vertical interface, which is like that. Sorry for my pictures, but it's an interface which is localized around the center, so around x1 equal to 0. And you see, this is now we can compare this fact with equilibrium. Namely, if you want to, and it's very well known that in equilibrium statistical mechanics, interfaces are produced by the boundary conditions. So in thermal equilibrium, you can put plus or minus boundary conditions, say left and right. But then to produce the interface, you have to also put the plus and minus like this picture, no? Plus up to here and minus here, and also below. In this way, you get an interface in the middle. So, in our case, we don't have plus and minus boundary conditions. And we had we didn't put any boundary conditions, just periodic top and bottom. And the localization, so it's due to the external magnetic field. So this, I want to read this by saying that it's somehow the current that localizes the interface in this case. I have not the boundary conditions. And actually, at this point, you want to ask yourself what's the difference in behavior of the interface in the nest and in the equilibrium. So I want to know, there are these two natural questions which arise, no? How much localized is the interface around the middle, and how rigid it is, in the sense, what are the size of these fluctuations? Okay, to this question, we have an answer in a paper with Merrill and Dolla, but in a solid-on-solid-on approximation. So we prove that in this approximation, the interface is much more rigid. So it's localized around x1 equal to 0 by the order of n to the 1/4, and also fluctuates by the same order. Okay, the extension to the true Gibbs measure is open, but we think it's the same, and the behavior is this one. And so the interface in the non-equilibrium stationary state is much more rigid than in thermal equilibrium, where it's well known that the fluctuations are of order n to the 1/2. Okay, so the next discussion is about, so I emphasized that before, that in the previous setup, we didn't put boundary conditions on the Hamiltonian. Instead, now I want to do that. So I want to consider this case. So I put minus boundary condition on the left, plus on the right, of instead of a square, I consider a rectangle. So the length is 2n, but the height is n to the alpha with alpha less than 1. I will explain later why I need rectangle instead of a square. And so now I have the easy Hamiltonian as this boundary condition, plus or minus, the one I have here. And the nest is as before, the Gibbs measure with this H, with plus or minus boundary condition, and with the slowly varying magnetic field. Then, as before, the interface is localized in the middle. Why is it so? But you have to, nothing changed with respect to before, in the sense that the influence in this Gibbs measure of the boundary conditions decay exponentially fast. And the magnetic field, this lambda, is positive on the right, no? Because when x dot E1 is n, this is lambda, no? It's positive. And then it's negative on the left. So it's the magnetic field that forces the interface, and then it's still localized in the middle. This is different from the equilibrium. Indeed, if you consider the same situation in thermal equilibrium, so the previous measure, but without external magnetic field, so lambda n is 0, and with same boundary conditions, the behavior is different. Remember that, okay, I go back. I have now in thermal equilibrium, this gives measure without this magnetic field. So I have the Hamiltonian plus and minus boundary conditions, but on top and bottom, you have periodic boundary conditions. So the behavior of the equilibrium is that the interface is not localized, but in the limit n goes going to infinity, it will be uniformly distributed in the space. And there will be over the rigid over the n to 1/2 s. This, I guess, follows, as was explained to us by Joffe, follows from the work of Joffe, Schlossman, Belen, and so on. Okay, I will come back on that. Okay, so, but so far so good. So if I put plus and minus boundary conditions and I keep lambda fixed, the lambda, this lambda, nothing changed really, no, with respect to the interface. Still is localized in the middle. But if I take instead this lambda small, some strange things happen. So that's the next slide. So what we study now is it's the case where this lambda is of order 1/n. And the difference now in the thermal equilibrium will always be, as before, the interface is uniformly distributed in the space. And instead, now the nest is much, it's different. And so I write here the nest again. So you have the usual Hamiltonian, as usual, the one as before. But now lambda, the external magnetic field, as A/n, and then so it's order A/n squared. Not really, because when this is n, this is order A/n, so the bound. And now I take the boundary conditions as before, no, in the Hamiltonian. So now the picture is the following. Here you have plus boundary conditions, but you have an external magnetic field which is negative, but is somehow small, and the opposite on the other side. Mm-hmm. So what I want to say now is, as underline, is that what happens is that we have these two facts. If A is large, there are three disjoint interfaces. And as I mentioned before, we proved that the current is negative, but the magnetization density on the left is larger than the one on the right. So the current goes uphill. It seems in contrast with the fixed law. So let me explain this. This is a resulting preparation and in collaboration with Joffe, Meror, and Presutti, which uses results from this paper that study very much related questions. And actually, the sudden death of Joffe stopped our work. We are sadly trying to complete it because we want to do it like he did, like he was planning to do. Okay. Okay, so the theorem we have is like that. You have an A critical. A is the parameter of the external magnetic field. And if A is small, smaller than A critical, then there is only one interface close with equal probability to one of the two boundaries. Instead, if A is bigger than AC, there are three interfaces. One is close to the left boundary, the other on the right, one around the center. And then they are disjoint. Okay, the stationary current, this is already established is negative. So why is this result? I want to conclude by explaining this theorem. The explanation is is well understood if you consider a toy model. A toy model is this one. So assume it's made of sticks, of these segments, and you can have any number of sticks. So I call the configuration of sticks underline x. I have x1, x2, xk if there are k sticks. And these xi are between less than n, but also real number, assume. Call k of x the number of the sticks on configuration of x, and then in the picture I used k of x in particular. Okay, so this is the setup for the toy model, and the energy is the following. So there is this part that is remembering of the interaction in the actual model. So you have the number of sticks, which is k of x, times 2m is the length of the sticks, the height, and tau beta is the easing surface tension of an interface parallel to the coordinate direction. Instead, the magnetic field, the previous lambda n, I put it, I call it EA of x, is equal to minus 2m, because still you have this length. And then it's the integral of this function. So lambda n is like before minus a over n squared z. And m of x is a piecewise constant function, which is equal to, like in the picture, m beta minus m beta and beta and minus m beta minus m beta, where m beta is the spontaneous magnetization of the existing model. So we are this toy model says that, I mean, you can have a number k of x of interfaces, say, then I put it as straight line, and the energy of the interface is made of two pieces. One is proportional to the surface tension of the interface, and the other is due to a magnetic field, which is slowly varying, but which and in between the sticks, you have the pure phases plus and minus. So for this toy model, you can really compute the things. I mean, you can do exact computations, and then you can prove the theorem that I stated before. You have an expression for AC and so on. The last thing I want to underline, and then I guess I'm out of time, is what is the problem? Well, the problem is that the proof we want to do for our real model is to say that the toy model is close to the actual model. I mean, the interface, in particular, I want to say that the interface are approximated by vertical sticks, that the magnetization between the sticks is the pure phases, and that the interface do not interact with each other and with the boundaries. And the fact that the interface are far away from the boundaries due to the entropic repulsion effect, and then it's essentially to explain the appeal diffusion. I mean, let me explain these things. I mean, so the situation is like this picture. So you have the assume now I have one interface. So the thing we want to prove is that the interface is far away from this boundary, and is far away of order n over n. This means that when n goes to infinity, the distance goes to infinity. So it's not attached to the boundary. And this is due to some entropic repulsion effect. Okay, we even know the distribution of this R. This is random, these are here, so the location, but uniformly positive with the probability going to 1 and sign positive. We actually know its distribution. Thus, in the green region, the state is metastable because the magnetization is positive, plus and beta, but the external magnetic field is negative. So the state, this is what is called metastable state. And so the main message is that metastability and this fact of the appeal diffusion are closely related in this sense. So sorry, maybe I did over time. Thank you very much for your attention.
Thank you, Anna. So are there questions from the audience? Okay, let me try to see because
we have one question from here on site.
Yeah.
So my question would be, do you have any guess for the scaling limit of the interface? And do you have dynamics in which these measures that you introduced will be the stationary states for that dynamics?
Yeah, let me answer to the second question. The Ising, what I call UN, the Ising case is the NES for the, sorry, I know that it's annoying that I go back, but so there is a model which is called phase field, sorry, yeah. Sorry. Okay, there is a model called the phase field stochastic model, where which is a combination here. I mean, the Gibbs measure, the one real Ising with this external magnetic field, is the NES for this stochastic phase field model. This is a stochastic process where there are two variables. One is a spin variable, the other is a Gibbs-Landau. So it's defined in such a way that the sum of the spin in X plus the Gibbs-Landau variables is constant. And then you can prove that the marginal of the spins of the non-equilibrium stationary measure is exactly this one. So this is the example. Then for the, I don't know, I hope I answered your question. This is a very nice model, actually. I like it a lot, but I didn't have time to introduce it. The other question is about the fluctuations. So actually, I mean, in the case of lambda fixed, this one, so we had this result for the SOS approximation. We were trying to prove the thing for the real model, but we did not succeed, but so far, okay. And instead for the case of three interfaces, we just did not even try, actually. But I mean, we are happy that they are far away. So we know the distance is at least n over n. But we don't know much more yet.
Thank you, Anna. Other questions?
There is one more, yes, on site.
Yes, thank you. I didn't know about these very nice non-equilibrium states out of equilibrium. I was wondering if you put a little perturbation to your dynamics, so you probably won't get the exact non-equilibrium state. But is there a way to I don't know, understand how this perturbation would affect them, or it's just one or nothing? Either you have it or you don't. I don't.
Let me answer in this way, that to prove that the NES is exactly that one, it's just a computation. I take the generator and then it comes out. Yes. There are some miracle cancellations that I don't know, that happens like that. So I don't know But I also want to ask to you which kind of perturbation you have in mind, of the Hamiltonian or right of the dynamics?
At the level of the dynamics, but I mean something which because what I was wondering, for example, if you look when you think symmetric simple exclusion, or you think other types of model, you have different long-range correlation which are imposed as well by the perturbation. So I was wondering in which, and I don't know which kind of perturbation what could handle, but if you do this perturbation, which way it will impact the NES, and whether it will enhance the fluctuation of the interface, or even more, maybe make it more rigid. But okay.
Yeah, I just asked Derrida and Leibowitz. They about this fact, the mysterious fact that we know the NES. They know. They say, I mean, in this theory of large deviations, no, that you know, that the chi, what was the compressibility in the Ginzburg-Landau model is 1, okay? And then they say, well, that's the reason why there are not long-range correlations. I don't know. It's let me leave like that.
Okay. So maybe it's a good starting point to have it 1 plus epsilon or something. Okay, thank you very much.
Okay, more questions?
I don't see any from on-site.
Okay, so let's thank Anna again. Thank you very much, Anna, for this nice talk. And now let's go to our second speaker, Claudio Landing. I think you are in presence. I just saw you. So it's my great pleasure to introduce Claudio Landing. I'm not sure we should stop a bit because maybe you have to prepare something or not. No, you are ready? Oh, you're ready. Oh, fantastic. Okay, so it's my great pleasure to introduce Claudio Landing from NIPA and the CNRS in Rouen. So Claudio received his PhD in 1990 from the University of Paris 7 under the supervision of Claude Kipnis, and his thesis was related to hydrodynamics and large deviations of particle systems. So Claudio, I don't want again to steal much time from your talk. Yes, I see you now. So let me, I mean, you don't need any introductions. You have a fantastic CV. So lots of students, many postdocs, and well, I was one of your PhD students. So I'm very happy that you are here. I'm very happy that you can be in person. And your talk today, so I'll go to metastability. And so you're going to talk about a resolvent approach to metastability. So before I forget, you're going to get a medal, Claudio. I think you will receive it there. Yes, there it is. Great. And well, Claudio, go ahead. The stage is yours. Thank you so much.
Well, thank you very much, Patricia, for the introduction. Thank you for the invitation, Funaki, Patricia. It's a great pleasure to be around. So I will speak about metastability in principle. I will organize my talk in 3 parts. I want to state a theorem. To state that theorem, I need to introduce a model just for you to have an idea of what we want to do. And after we state the theorem, then I will try to give some applications. So I'll start with a model, then some theory, and at the end, some applications. If it's not clear, please interrupt me, ask questions, feel free. So I start with a very simple model to make things clear. So what we want to do is coarse graining. So we start with Markov chain. Say here I consider a random walk on this space. So you have squares of cubes of any dimension which are linked to each other by 1 point. So let's take to fix idea squares. So these are squares n by n, and these squares intersect at 1 point. And you have a random walk evolving on this space, which means that at each point it waits a mean 1 exponential time, and then it chooses with equal probability one of the neighbors, and it jumps to that neighbor. And this is the dynamics. Okay? This dynamics, it's very simple. It's stationary state. It's known explicitly. And it's what I represented by pi n. So I will represent the configurations by eta. So the degree of eta, it's the number of neighbors. And the invariant measure, which is reversible, actually, is proportional to the degree of the point, the degree of eta, the number of neighbors. And of course, if you see that, what you'd like to do is to coarse grain, to say that, well, these dynamics will be well represented in some time scale by a four-state Markov chain. So theta n will be the time scale at which you will observe an evolution among these four squares. And the problem is to make sense of that. So we would like to say that essentially what you're seeing, it's a four-state Markov chain. And we want to describe what is this four-state and how to make a formal description of what we mean by this coarse graining procedure. So this is the problem. So in this model, there are two time scales which are very important. The first one is the mixing time. So let's say that you take one of these squares, which is n by n. You start from a point, an inside point, and you ask yourself, well, how long do I need to wait until the distribution of this chain is very close to the stationary distribution? And this is well known. The mixing time, it's n squared, whatever the dimension. So this means that if you wait time of order n squared, you are close to the stationary state, which in particular tells you that you lost memory. You don't know where you started from, because now you are very close to the stationary distribution. So in this model, you lose memory in the time scale n squared. But then there is another important quantity, which is, well, the time at which you reach one point. So you fix one point. How long do you need to wait until you hit that point? And this is dimension dependent. In dimension 2, you need to wait n squared log n to hit a point, while in dimension d larger than 3, larger or equal than 3, you need to wait n to the power d. So this means that if you start your process from a point, after time n squared, you're close to equilibrium, so you are somewhere in the square closed uniform, well, measure which is proportional to the degree of the points. And then, well, if you want to go from one square to the another square, you have to wait a much longer time scale, let's say, n squared log n in dimension 2. And then once you reach this point, so this intersection point, what you will do is small excursions around this point until you do a long excursion. When you do this long excursion, you will be far from that point. So you will wait a new n squared time until you reach equilibrium, and then a new time n squared log n until you hit that point again. So what would you like to do? Well, say that first project. So this is the function psi. So it's, if you remember, we represented by these squares by E0n, E1n, and so on. So psi will just project the point, the configuration, to the index of the set. So if you are on set E1n, if eta belongs to this set, psi will give the value 1 to eta. So this is the projection. And then you'll consider the evolution of the projection. Of course, the evolution of the projection, it's not a Markov chain anymore. It's a hidden Markov chain. And, well, you'd like to show that in this time scale theta n, which here will be in dimension 2 n squared log n, that you expect to show that this converge to a Markov chain, which I'm calling xt. Yt, sorry. But if you go to the path trajectory, what you see is that, well, you stay a very long time of order theta n, which in our example, it's n squared log n in these one set. So psi, it's constant, until you hit this intersection point. At that point, you do this small fluctuation. So your process will jump from 1 to 2. very often in a very short time scale. And then it will go far apart. And at that point, you need, again, a time theta n to return to this point. And again, you do these small excursions. So the typical trajectory will look like that one. And of course, if you want to prove some convergence, well, this is no good. That will not converge in, say, this Korahot topology. So if you want to prove convergence in this topology, you need to do some surgery. And this is what I will explain next. So the idea here is to take the trace of the process in a small set. So let's say that now I define these blue sets, which are the bulk of these sets. Well, the picture is not very good because what you're taking out of the square, it's, let's say, a portion of square root of n of this set. So you take a neighborhood of the boundary of square root of n, you remove that very small set, you get the bulk, which is the blue, which essentially contains all points. And what you do, it's, well, I want only to observe the process while it belongs to these blue sets. How you do that? Well, by defining the trace. So the trace works as follows. Each time you leave the blue set, you stop your clock until you return to the set. So to illustrate that, we have this left-down picture in which you have a typical trajectory. So you started from, say, a point A, and you have the set E. Let's say that you want to take the trace on A, the set made of A and B. So you started from A, you spent some time there, then you jumped out of the set AB. You jumped, you returned to A, you jumped out, you returned to B, and you jumped out. So what you do is you remove from your trajectory everything which is out of A and B, and you push back to have a trajectory in AB. So this is what you do. So this is what I'm calling the trace of the original path on the set AB. It's what we call the trace of the process on the subset F. So if you want to define that formally, what you do is you define this set T, this function T, which is on the right down corner, and it essentially tells you what time you spent on the set F until time T. And what you do is that you change your coordinates. So instead of looking at time on coordinate X, you look at it on coordinate Y. So this is what you do. And what's, so if it's not clear, please let me know and I'll try to explain. But so what's very interesting about this trace process is that you still have a Markov chain. So you started from a Markov chain. You take the trace of this Markov chain on a subset F, and the new process you observe, it's still a Markov chain. Now the state space, it's this subset F. And what's slightly complicated is that if you want to compute the rate at which you jump from a point to another, well, you can only express it in terms of heating times. So this is my last line. You have RF, let's say the rate at which the trace process jumps from a point eta to a point psi. It's given by the holding time of the original process, which is lambda of eta, times the probability that starting from eta, you return to the set F at the point psi. So the annoying point of the trace is that, well, the rate jumps are now expressed in terms of heating probabilities. Okay? But what's very nice is that this is a trace process. And you see, now you may have long jumps. So I hope you can see these red points. So for the trace process, it's possible to jump from one red point to another red point, right? Because you just leave the set and you return to the set on that point. Fine, so I define the trace process, and now I can well, define what we will understand by metastability. So let's say that we have a set En. So we define this subset Exn. These are the blue sets. I will define by En the union of these subsets, and by delta n what remains. So what we achieved by taking these subsets is that we don't have this problem anymore that our trajectories jump from one set to the other. Because once you reach the blue set, you will equilibrate before you hit another blue set, a different blue set, right? So if you look now at the trajectories of the trace process, they don't have these small, very fast jumps between two different sets. And so now let me project. So I'm first taking the trace. I'm taking the trace. I project the trace. This is what phi is doing. Phi is projecting from the set to the index. And I will say that the process, it's a process or a sequence of process, it's metastable if it has two properties. The first one, which is what I call the condition C, it's that, well, this projection in certain time scale theta n will converge to a Markov chain xt. So this is the first condition. You're asking that the projection of the trace converge in some time scale. And then, well, you removed from your state space this set delta n. So what you have to ask is that you don't spend too much time on this set delta n, which we removed. Because, if you remove a very large set, you're not coarse graining anymore the original process, right? So we will require as a second condition, this condition D, that, starting from a point on your space En, so one of these blue sets, the total time you spent on the set you removed, that is delta n, is small. And this uniformly from the starting point. Okay, so this is a definition we proposed with Beltran. And what can we show from that? Well, two things. So we proved with Loulakis and Mouhagi that if we are able to prove these two conditions, C and D, what we can show on the first hand is that, well, the projection of the original process converge, in the sense of the finite dimensional distributions, converge to the finite dimensional distributions of your process xt. Okay? So remember, we wanted to prove converging the Skorha topology, but now if we remove, well, we don't bother with the Skorha topology, we just look at the finite dimensional distribution, then we get as a corollary of these results, well, of condition C and D, that the finite dimensional distribution of the original process converge. And also what one usually would like to understand as metastability is that, well, if you start at a point, you let your process evolve at this time scale theta n. At time t theta n, you have a distribution, okay, on the total space, because now we are talking about the original process. Well, what is this distribution? This distribution can be described simply by saying that, well, what you see is that, let's say that you take one of these squares, you consider the dynamics restricted to that square, so a random walk on that square. You look at the stationary state of this restricted dynamics, which is the measure I introduced below, which is proportional to the degrees. Well, the distribution you see at time t theta n, it's a convex combination of these stationary states to the restricted dynamics. And what is the weight? Well, the weights are given exactly by the transition probability of the process xt. Okay? So you have a description of the distribution in this time scale. Fine. Well, the problem is that if, so we developed a theory to prove these two conditions C and D. The problem is that these conditions, to prove these conditions, we rely on explicit computations on the Markov chain. So you have to compute capacities and explicitly in order to prove. And in particular, to compute these capacities or these variables, you need to know explicitly the stationary state of the process. So all techniques which we know up to now, in order to derive the metastable behavior of a sequence of Markov chain, relies on explicit computations which requires the knowledge of the stationary state. So here, with Diego Marcondes, which is a PhD student at the University of São Paulo, and Insuk Siu, which is at the Seoul National University, we proved the following result. Let me just check time. How much time do I have? Because it's 5 minutes. Okay. So, okay, no, that's fine. So let's say, what did we prove? So we still have the same setup. So we have this set En, which is divided on these blue sets, and delta n is what we remove from our state space. So what we claim is that under that condition D, which means that you don't spend too much time in this set delta n. So let's assume that we know that. So we remove the set which is small in this sense. You don't spend too much time on this set. So what we prove is that metastability, so a necessary and sufficient condition for metastability is the following one. So let's say that you start with a function g, which is defined on the projected space, S, which in our case was 0, 1, 2, 3. Now, let's define by Gn the function defined on En, which on the set Exn takes the value of Gx, and which is 0 on delta n. So we have a function which is constant on these blue sets and which is 0 outside of these blue sets. Now, define Fn, denote by Fn the solution of this resolvent equation. Okay. So assume that you can prove that on each set, on each blue set, this solution of this resolvent equation, Fn, it's constant, and that it's asymptotically constant, and that the asymptotically constant is itself the solution of the resolvent equation, where now L is the Markov generator of the projected, so the asymptotic dynamics, that the limit is the solution of that synthetic resolvent equation. So if this is true for all g and all lambda, then the process is metastable. Okay? And this is a necessary and sufficient condition for metastability. So now we have a condition which, well, for the first time, it's necessary and sufficient, and on the other hand, does not rely on the stationary state. It's just, well, you have to solve an elliptic equation, in the case of a diffusion, and prove that the solution of this elliptic equation has certain properties. So we have a stochastic phenomenon which is now translated into an analytical property of solutions of certain equations. Okay? And one possible application we had in mind, it's a very simple and still an open problem. So let me give it to you. Assume that you have a vector field B and consider the dynamical system x dot equal to b, x. Well, assume that this is defined on a finite bounded domain, and assume that the drift points down inward at the boundary, so you're constrained to this set. Assume that, say, to fix ideas, that you have two stable points and one unstable point. Now, add some noise. So let's take that W to be Brown in motion. Consider the perturbation in which you add this noise to your dynamical system. You would like to show this is an open problem, as I said, that your process, now it's metastable between neighborhoods of these two stable points. Okay? Well, if B is given by a gradient, so if the gradient of some potential V, then this is known. But in general, this is an open problem. So now maybe you want to show that the solution of the Resolvent equation for this process, so you write down the generator of this process, you have this operator. Now, proving that the process is metastable consists in showing that the solutions of the Resolvent equation associated to this operator are constant in the neighborhood of these two stable points. So maybe one can try to develop analytical tools in order to show that, and from that conclude that your process is metastable. Now, let's say that this condition might seem maybe too stringent. Let me say that it has been proved for a large class of systems, so from statistical mechanics. So here I quoted some. We have random-walks-in potentializing pots, Bloom-Capell models, condensing zero-range process, and a few others. So, okay, since I had only 10 minutes, maybe. Okay, well, no, thanks. So let's go to. So maybe I'll skip. Maybe I'll skip a part of, let's say that with Beltran we developed tools from potential theory which permit to prove the metastable behavior of some Markov chains. And so I won't spend time here, but let's say that we had these two conditions, H0 and H1, and we proved, and other people proved also that. So what we proved is that these two conditions entail metastability in the sense I defined, and what people did is to prove that all these models I mentioned satisfy these two conditions. And what we can show is actually these two conditions also prove that the solutions of the Resolvent equations have these two properties I mentioned. So actually, these property of the solutions of the Resolvent equation are satisfied for all systems which satisfy these two conditions, H0 and H1, which have been proven for many models. And let me end with one. So I started with maybe an artificial model, but just to explain the content of our result. So let me introduce another model which is more interesting, so the condensing zero-range process. So here we fix L sites. We have particles moving in these L sites. N is the number of particles, and it will increase to plus infinity. So the configuration will be represented by eta. Eta x will be the number of particles at site x for the configuration eta. And the dynamics is as follows. You have a function g, which is defined on the non-negative integers. And you have a transition probability here to fix ideas. I'll just take p, a parameter between 1/2 and 1. And what you do is, well, at rate, if you have k particles at a site, at rate g of k, one of them will jump. And here, say, with probability p to the right and probability 1 minus p to the left. And this defines conservative dynamics, so the total number of particles is conserved by your dynamics. And what's interesting in this model is that if you take a special g, so let's say you fix alpha, a positive number, and you say that gk is equal to k divided by k minus 1 to the power alpha. So mind that this is converging to, it's decreasing to 1 as k goes to infinity, and it's decreasing, so the more particles you have, the less they jump. And what's interesting in this model is that you have a condensation phenomena. So which means the following. It means well, let's say that you start with an equal number of particles at each site. You let the process evolve. what you will observe is that all these particles will condensate on one side, which means that the stationary state for these dynamics is a measure which is concentrated on configurations which essentially all particles sit on one side. So this is what's called the condensation of this class of zero-range process. And then what you are interested in is, let's say that now you start from all particles on one side. There exists some time scale at which you observe an evolution of this condensate, right? And so this is a model which enters exactly in this theory we built. And it has been proved by several authors that if alpha, the parameter I fixed, it's strictly larger than 1, then in the time scale n1 plus alpha, you'll see this condensate evolve. And let's say that you start in a torus with nearest neighbor jumps. A natural question is to say, well, how the condensate will evolve? Well, what we proved is that the condensate evolves according to a random walk on this torus, but which now jump from x to y with a rate which decreases as the inverse of the distance from x to y. This was proved for alpha larger than 1, because essentially you can, before you leave one of these wells, you visit all points of this well. This is not true for alpha equal to 1. And with this resolvent method, we are now able to extend these previous results to the case in which alpha is equal to 1. So thank you very much for your attention.
Other questions from the audience?
Sorry, maybe I have a question. So far, the way you've been checking this new resolvent condition is by using the capacity of the previous paper you did, or can one check it directly?
Okay, so no, what we proved, as you mentioned, that these two conditions imply that the resolvent condition is satisfied, and since they have been proved for many models, we know that the resolvent condition is also satisfied for these models. What have been done directly, it's in this case alpha equal to 1, because this condition H1, it's not satisfied anymore. Condition H1, which is stated in terms of capacities, imply in particular that the process visits all points of the well En before hitting a new well. This property is not satisfied in the case alpha equal to 1 because these wells are very much larger. So in alpha equal to 1, we proved directly that this resolvent condition is satisfied. And this is also has been shown for alpha larger than 1 by Rosen-Kalou and Hao directly.
Okay, thank you.
Are there more questions from the audience?
I don't see question on site. Do you have question online?
No, online, no. So Claudio, I have a quick question. Yeah. In your first example, which was a two-dimensional random walk, symmetric random walk. So in terms, if it was not symmetric, could you say something? So if it was partially symmetric? And another question has to do with this. You said that you have to remove a square root of n around your box. Is this choice particular for the symmetric random walk, or you just need really to have a little slice of the box out so that your condition holds?
Well, it has to increase in n, and it has to be smaller than n. But anything in between is okay. Then, well, actually, we didn't prove the metastable behavior for this model because the capacities will be complicated to compute. So even less for the asymmetric. So I just introduced this model to present the theory, but Okay, I believe it's possible, but though I never checked it.
Thank you. Okay, so normal, okay, wait, I think there is a question. Yes, there is a question, so let me just quickly read it for you, Claudio. So it says the following: your resolvent condition suits for the case in which the limit metastable process is Markov. Is any general condition known which ensures this Markovianity?
No, what I can say is as follows. Well, if you take the same model, but instead in 2 dimensions, you take 1 dimension, and so you have these lines of size n which have 1 point in common, then the asymptotic process will not be Markovian. So it's an example in which the limiting process will be a renewal process, but not a Markov process. So, well, the theory has not been extended to these more general models, but there are some examples in which indeed the limiting behavior is not described by a Markovian dynamics, but by a renewal process.
Okay, very good. Okay, I think there are no more questions from here. Okay, so let's thank Claudio again. Thank you so much for the nice talk.
Thank you.
Thank you. Okay. Hao, I think you are here.
Hi. Should I?
Yes, yes. Yes, you are here. Okay, so now we have our third and last speaker of this session today. So we have with us Hao Shen from the University of Wisconsin-Madison. Okay, we're a bit out of time, so I try to be fast. So Hao, it's my great pleasure to introduce you to this conference. So let me just tell you 2 lines about your CV, just to be really short. So you finished your PhD in 2013 under the supervision of Weinman, and you worked on, so the thesis was about normalization theory in statistical physics and stochastic analysis. You have many research interests from stochastic PDEs, probability, and stochastic analysis. And so today you decided to pick a topic about the large n limit of stochastic PDEs. So don't forget, you're going to receive a medal for being an invited speaker. So at some point you will get it in your mail. And go ahead, Hao, the floor is all yours. Thank you so much.
Okay, thank you very much for the invitation, and thank you for the organizers. I'll be talking about large n limit of stochastic PDEs. This is based on joint work with Scott Smith, Rongchan Zhu, and Xiangchan Zhu. So the theme of this talk is that, in some of the Euclidean quantum field theory models, the fields take value in n-dimensional space. So the question here is, what's the asymptotic behavior as n goes to infinity? In this talk, I'm going to use stochastic quantization formulation to study such questions. Basically, in Euclidean quantum field theory, a model is defined via such a measure on the space of fields phi. And you can view this as an equilibrium measure. And the stochastic quantization is a procedure to turn this equilibrium problem to a non-equilibrium problem, to turn this into non-equilibrium dynamics, which is usually stochastic PDE. So the advantage of using stochastic PDE to study such quantum field theory models is that, okay, once you have PDE, we can exploit a lot of mathematical tools, such as PDE theories, stochastic analysis, and in this particular question of large n, we also have mean field theory tools. So I'll start by the simplest quantum field theory. This is called phi-4 quantum field theory. It's actually very similar with the Ginzburg-Landau model mentioned by Professor De Masi in the first talk. So this exponential of action, where the action has a quadratic term and a fourth order term. The lambda is a coupling constant. If lambda was 0, then this would be called the Gaussian free field with the mass m. Stochastic quantization looks for a dynamic such that the okay. First of all, this is a formal measure because when the dimension d is 2 or higher, this would need a renormalization. So formally, the measure here would be invariant under this dynamic. So this is called stochastic quantization. In particular, the drift term here in this equation is precisely the gradient of this action. And the last term here is a space-time Y noise. So stochastic quantization is not new for physicists. It goes back to Parisi and Wu. But again, the reason that we use this dynamic to study this sort of quantum field theory is that we can, we have differential equations and so on. We have analysis tools. Okay, so the model I'm going to talk about in this talk is a vector generalization of the phi-4 model. So here, the phi has n components, and n will be large. And now the model is again defined by exponential of this action. And if the coupling constant lambda was 0, this would be n decoupled Gaussian free field. But with the last term here, this last term is interaction between the different components, because this is natural generalization of the phi-4, right? So this is the sum of phi square. So it's there's product between phi I square and phi j square. So the interaction here. And then this term is divided by n, so that at least formally all the terms have the same order. Now we look at the stochastic quantization of this model. Again, we take the gradient flow perturbed by Ci. Now the Ci's are n independent space-time Y noises. And this is a system of coupled stochastic PDEs, because the I's equation here depends on the J's equation from this coupling term. Okay, now we have n equations, and here we have n fields. The basic question here is asymptotic behavior as n goes to infinity for both the equilibrium measure and the non-equilibrium dynamic. In other words, we study the mean field limit of this model. Okay, so before I describe what kind of results we can obtain, let me just quickly mention some background. So in physics, there are a lot of study of large n problems, of course, non-rigorously. Okay, so first of all, there was a study in statistical physics. So Stanley studied a class of spin models with n components, and turns out that as n goes to infinity, it converges to a solid model called spherical model. And he also studied like 1 over n expansion of certain observables in this model. And then in quantum field theory, this was studied by Wilson, Gross-Neville, and so on for this sort of n component phi-4 model, which is the model we discussed today, and also some fermionic models. And then an important work by de Hooft used the same idea to study Yang-Mills model, where the gauge group has dimension n or n squared. So, and then he realized some duality to string theory. And then this Witten also studied nonlinear sig model, where the target space is an n-dimensional manifold. So after these works, huge literature in this direction. But there are not many rigorous results. Let me just mention a few of them. So there's some study about Yang-Mills model in 2 dimensions, but this crucially relies on some sort of integrability structure of Yang-Mills in 2D. So that's very specific to Yang-Mills in 2D. And then more recently, Chatterjee and Javarov studied Yang-Mills model on large N problem, Yang-Mills model on the lattice. But here the lattice is a great simplification. As you're going to see, the continuum questions will be much harder than lattice. Okay, and another work by Kupiainen back to 80s is more relevant to my talk. I'll mention his result later. So let me describe what kind of theorem we can prove. The first theorem is about non-equilibrium, so it's about a dynamic. We consider two-dimensional torus, and this is our coupled system of SPDs. What we prove is as n goes to infinity, the solution phi I converges to a very interesting limit called psi I. The psi I here satisfies the following self-consistent stochastic PDE. Okay, so first of all, this equation for the limit psi is decoupled. You can see that I's equation does not depend on any J component. And the leading term here is again a heat equation. And this term here, it looks like a linear term in psi I with some coefficient. However, it's not really linear because this coefficient depends on the law of psi. So this is actually the variance or renormalized. Okay, here the dot means the renormalization, which I'll tell you later. But basically, this is the variance or renormalized variance of the solution psi. So this is a very natural dynamic. It's a heat equation plus Y noise, and then a linear term with coefficient being the variance of the solution itself. And this result is reminiscent to mean field limit in in the vast math literature on this sort of mean field limits. But usually these sort of results are for stochastic ODE systems or for n interacting particle systems. And as n goes to infinity, usually people could prove some sort of McKean-Volossov process in the limit. Okay, but as far as we know, this is the first sort of mean field limit results for singular stochastic PDEs. Singular means this sort of SPDs need renormalization. I'll tell you what's that later. So this is our first result about the mean field limit of dynamic. The second result is using the dynamic, we can prove the large N limit of the Coulomb field theory. Here we can prove this result for on both two-dimensional, three-dimensional torus, but there's a technical condition which is we should assume that the mass is large or the coupling constant is small. This might have some physical reason because this sort of model has, I think, has some phase transition. Okay, so our result shows that as n goes to infinity, the measure here converges to Gaussian free field, which is just the first two terms. Okay, so the first two terms is like Gaussian free field with covariance being m minus Laplacian minus the Green's function Laplacian. So heuristically, you can understand this as, okay, as n goes to infinity, the interaction term would vanish in the limit. It would just disappear. But this, for this to happen, this interaction must be renormalized. Okay, in 2 dimensions, we can renormalize it. In 3 dimensions, it's more sophisticated. Anyway, so let me remark that this Gaussian free field behavior in the large N limit was actually predicted by perturbation theory by physicists, of course, in a non-rigorous way. And the physical argument was that, okay, they basically do some Feynman diagram expansion for this model, and only the leading order, or in the physical language, zero loop diagrams for the correlation functions are order 1. All the higher loops Feynman diagrams are of order 1 over n or even smaller. And this is why they believe the correlation function should behave like Gaussian in the limit. Okay, but this first time rigorous proof this. As another result, we also look at observables of this model. This model has a natural ON symmetry because here the field is a n vector, and if you do a rotation on Rn, the measure is invariant. So a very natural observable to look at is actually not the field itself, but the this sort of observable which is invariant under rotation. This is just the square length of this vector phi. Okay, again with some renormalization. Right, so the sum of phi squared. Now I also suitably normalize that. And I look at a 2-point correlation, for example, of this observable. We can prove that as n goes to infinity. Okay, first of all, for finite n, it's impossible to have a formula for the correlation for finite n because this model for finite n is it's not a solvable model. But turns out that as n goes to infinity, it has some solvability structure. Namely, the limit of this 2-point correlation has this exact formula. And here the C is a Green's function for Laplacian, and the hat is a Fourier transform. So this formula is Fourier transform of 2-point correlation. And actually, let me mention that this formula is pretty non-trivial in the sense that if you remember the previous theorem, we showed that the limit of this field phi is a Gaussian free field. So you might think that if you would just replace this field by the Gaussian free field, right? This is my remark here. If Zi are just independent Gaussian free field, then just consider the same observable but with phi replaced by the Gaussian. Then computing you can compute the correlation exactly by Wick theorem, and the correlation is always equal to 2c squared. But then this is different from this result. So this means my correlation formula in the limit is different from what you would get by just replacing the field by Gaussian. Okay, so the field has Gaussian limit, but this observable has a limit which is different from the observable constructed from Gaussian. Okay, this sort of formula was also predicted by perturbation theory by physicists, and also rigorously proven by Kupiainen in the paper I mentioned before. But I think this paper only assumed that the field converges to Gaussian free field. Let's just put this as an assumption. Okay, so for the rest of the talk, maybe I only have another 15 minutes or so, but before the proofs, maybe I can pause for a few seconds for questions. Oh, okay, so I can just proceed to the proofs. Let me just first provide some stochastic Pde background. As I said, we consider this sort of quantum field theory in the continuum, and this poses a great challenge because in continuum, the fields or the solution to our equations are very singular. They are actually distributions, not just the continuous functions. And this is why we want to explore the recent development of stochastic PDEs. But let me just recall some background here. I'll just briefly describe how we deal with this sort of stochastic PDE when you only have one component, n equal to 1. So this is the phi-4 equation, the heat equation plus a nonlinear term plus the space-time white noise. And when dimension is 2, the solution is a distribution, so the nonlinear term is ill-posed. The idea here is to, okay, so the idea here is lambda was 0, then the linear equation was very well understood. So we just decompose the solution into z, which is the solution to the linear equation plus the remainder. And we substitute this ansatz to the equation, then we can write down the solution for y, the equation for y. Y solves the heat equation, and then z plus y cubed, so you get y cubed cross term y and z cubed. We can show that z is a distribution. In fact, z is explicit because z is basically heat kernel convolution with the noise. So we can prove z has regularity below 0, and here this space is the usual Bezoff space. And now, in particular, the z is Gaussian. So we can renormalize the powers of z using standard Gaussian moment calculation. And what we know is all these terms, all the powers of z belongs to this space C0 minus. And then using a standard fixed point argument, we know the y equation has a local solution. And the solution y actually is almost C2, is smooth. This is due to a Schauder estimate from PDE, which tells you that Laplacian give you 2 more regularities, so 0 plus 2. So the conclusion is for this equation, we have a solution phi, which has 2 parts, a Gaussian and a singular part, and the implicit part, but more regular. Okay, so this fixed point argument only gives us a local solution. How to extend to global solution? For this, we need some a priori PDE estimates. The idea is very standard in PDE. Basically, just integrate against y on both sides and over the torus. So when you integrate the left-hand side against y, you get L2 norm of y. And y cubed multiply y and then integrate becomes L4 norm of y. And then you see this minus sign here becomes crucial because now I put this L4 norm on the left-hand side, and then this is plus sign. This will help. So basically, the minus y cubed is a strong damping term, so that we can have very good a priori estimate for this solution over a long time. This is the reason that we haven't extended such a result to other quantum field theories such as Yang-Mills, because for those models we don't have this nice dissipation term. Okay, now we have the other term, cross term and z cube integrate against y. So this bracket is just the L2 bracket over torus. The idea is to bound these terms by a small coefficient of the L2 norms and the L4 norms, and then we can absorb these terms into the left-hand side. In this way, basically we have the derivative L2 norm is bounded by some constant. So we have a conservation of this sort of norm, energy conservation, so we can construct global solution. Okay, this is what happens for n equal to 1. And by the way, as I mentioned, that by studying such PDEs, we can have some results. We can say a lot about the quantum field theory. Just give you an example. So Moore-Weber used this idea to give a construction of 5-4 quantum field theory by averaging the law of the solution of the SPD over a long time, send time to infinity. So this is, when time goes to infinity, we obtain invariant measure, which is a quantum field theory. Okay, so very briefly So how much time do I have actually?
I think about 5 minutes.
Yeah, 5 minutes.
Okay, so I'll very briefly describe the proofs. So let me first mention that what I described here, the strategy for n equal to 1, easily extend to fixed n. And now we also need some understanding about the limiting SPD. So how to deal with this limiting? So this is still nonlinear, as I said, and the psi is again distribution. So the idea is, again, we want to decompose the psi into z plus x, where z is again the linear solution. So there's a similar idea as before. And then I need to tell you what is the renormalized variance. We define this renormalized variance of the psi by the variance minus the variance of the linear solution. In fact, both variances diverge, but somehow the two divergences cancel out, and this whole thing is a finite variance. Now, since psi is z plus x, we can write this as this, x squared plus 2zx. So the x here, the remainder x here, would satisfy this equation. To prove the mean field limit, now we have a phi decomposed into z plus y and the psi decomposes z plus x. Now we need to compare the y equation with x equation and show the difference goes to 0. A difference under expectation is important, and the expectation goes to 0. So the y equation again has a cubic term in y, cross terms and z cube terms, and the x. So when we compare them, since both equations are nonlinear, we also need some good control on each of them. So we have uniformly n estimate for the y equation. We have a priori estimate for the x equation, the limit, and then we can control the difference between y and x. I'll skip these details. So to prove the convergence to Gaussian free field for the quantum field theory, we consider the stationary solutions for both phi and the psi equation. A very important observation is that the linear solution is actually a stationary solution to the limiting SPD. So actually the Gaussian free field here is an invariant measure for the linear solution. So why is the linear solution, why Z solves the limiting SPD? Because this is how the renormalized variance is defined. If psi is just equal to Z, then this renormalized variance is equal to 0. So this nonlinear term disappears, and we have precisely the linear equation. So the phi is equal to Z plus Y. So to prove the convergence to Gaussian free field, we just need to show Y converges to 0 in the large n limit. And this is the following lemma. In fact, what we prove is that the quantum field theory converges to Gaussian free field in the at the rate of 1 over square root of n under the Wasserstein distance. The correlation formula was first derived, to derive this formula, we first used the Dyson-Schringer equation, which relates the 2-point correlation with 4-point correlation and a 6-point correlation. And then using the a priori PDE estimate, we show the 4-point correlation and 6-point correlation terms go to 0 in these Dyson-Schringer equations. And that's how we obtain this 2-point correlation forming a limit. Let me end the talk by a few future questions. We consider the model on the torus, but it would be nice to extend to entire space. And it would be nice to generalize our method to other quantum field theory models or systems of stochastic PDEs. And finally, so what about coupled KPZ systems or some sort of discretizations of this. For instance, interacting particle systems with n species. What's the asymptotic behavior as n goes to infinity? Okay, I'll just stop here. Thank you very much for the attention.
Thank you, Hao. Okay, are there any questions from the audience? So online, I don't think.
I was wondering about your theorem, page 6, I think. So, so in some sense, you show that in the n goes to infinity limit, the lambda parameter. Okay, no, maybe page 7. Then sorry. Yes. So in the n goes to infinity limit, the lambda parameter doesn't play a role anymore. So I guess because of this term, sum of the phi I squared goes to a constant somehow. And I was wondering what would happen if you would add mu over square root of n times the fluctuation given by that quartic term. Would it give an interesting limiting field, or by sort of combining theorem 3 with this theorem 2?
Oh, you mean in the measure? Here we
yes, in this Gibbs measure.
Parameter mu or something like mu, right? Times this. Okay, divided by. Okay, basically you want to add this term, this sort of term, into the action. I never thought about that, but it's actually very easy to make a guess using the perturbation theory, like what the physicists do. So basically, perturbation theory just means you just Taylor expand this exponential to whatever here into polynomials. So the Taylor expansion would be like 1 plus this term plus your term, and then plus square of such terms. And then the correlations can be exactly computed order by order, right? So because if you have just product of many Gaussian random variables, then you can use Wick theorem to compute it. And but I need to you need to sit down and do this computation to see basically what kind of Feynman diagram would survive in the limit.
Okay, thank you.
Thank you. Are there more questions from the audience?
I don't see one more question on site.
Okay, so online, let me check.
Okay, so
no, I don't think so. So let's thank. Yes, Tadahisa, go ahead.
So one page before you have a theorem 1.
Yes.
Does it imply the propagation of chaos? That is, if the initial value is almost independent, then the noise term is independent, of course.
Yes. So yeah, that's a very good question. We haven't been able to prove propagation of chaos in this case. The reason is actually very technical. So basically here, when we prove this, we assume yeah, we need to assume the basically initial condition of these guys are ID.
Okay, I see.
Yeah.
No, not close to independent. No.
No. But yeah, that's something we have been. That's something we're thinking about actually.
Okay, thanks.
Okay, so if there are no more questions, let's thank Hao and all the speakers of this session. Thank you so much for the nice talk. So thank you all for being here. So remember, next session about non-equilibrium statistical mechanics is on Thursday at 2 p.m. And I would like to thank everybody for being here, and I wish to see you soon.